In this chapter, thermodynamics, till now we discussed about the different foundations of thermodynamics, terms that we use in thermodynamics, and also about the different kind of processes. But in today's session, I will tell you about the first law of thermodynamics, FLOT, first law of thermodynamics. So how to derive the first law of thermodynamics and how to apply the first law of thermodynamics for different type of processes. What kind of numericals you will see from this first law, that we will discuss in today's session. So come, let us study about the first law of thermodynamics.
Hello students. So now we shall start our today's class for the first law of thermodynamics. In the previous sessions, we discussed about the different aspect of the thermodynamics, different terms we used in the thermodynamics, and various other parameters, state variable, path variable, and the foundations of the thermodynamics, which term we use in the thermodynamics, and what are the different kind of processes that we studied in the previous class. Now in today's class, we shall start with the first law of the thermodynamics. In short, we will call it as a FLOT, first law of thermodynamics. So what is the basic statement and the explanation of the first law of thermodynamics? It states energy can neither be created nor be destroyed. Only it can be converted from one to another form. This is the basics of the first law of thermodynamics. So if energies cannot be created or destroyed, the total amount of energy in the entire universe is constant. Whenever a given quantity of energy of one kind disappears, if any kind of energy disappears, then the equivalent amount of energy, same amount of energy appears in some other kind. So if one kind disappears, there is a development of another kind. Total energy remains constant, and it is not possible for a perpetual motion machine do work without consuming some form of energy. So no machine can work without expenditure of energy. Alright. And total energy of an isolated system remain constant. If any system is isolated, isolated I explained you in the last class. Isolated means no work done, no heat transfer. Then energy remain constant. So now we shall discuss the mathematical expression of the first law of thermodynamics. Now you consider an ideal gas in a cylinder which is fitted with the weightless and frictionless piston. Now you imagine there is a piston which is weightless, although it is practically not possible, but you have to imagine it, and also frictionless. There is no force of friction, and U1 and V1 is the initial internal energy in the beginning, and also the volume. Similarly, U2 and V2, they are the final internal energy and the final volume. The change in internal energy is equals to heat plus work. Now suppose internal energy of system initially is U1 and we did W work over the system. Change in internal energy, which is du. If some work is done on the system, plus W, and by heating the substance means heat is supplied to the system, plus Q. So the change in internal energy will be equal to the heat given to the system and work done on the system. So change in internal energy delta U is Q plus W. This is the expression of first law of thermodynamics. It changes with the condition. Like in this, we assumed heat is given to the system. Now if heat is released by the system, this Q will be negative. And same goes with the work. Here we considered there is a work done on system. But if there is a work done by system, then the same work will be negative. Now these are the sign conventions of thermodynamics. Internal energy. If energy is absorbed, final energy will be more and initial will be less. So it is positive. So always please take note of that. Whenever heat is absorbed, change in internal energy is positive. And when heat is released, definitely final energy U2 is lesser than initial energy, because now heat is being released and it is considered as negative sign. See, the sign convention of heat is same for all. That means chemistry and physics. Although there is a little change in sign for work that we shall discuss later. So Q, that is heat, if it is absorbed, it is considered positive, and it is released, it is considered negative. Please take note of that. This is something really important, and I want you to please memorize this. Always remember this. Now, work done. Like I said, work done. In chemistry, we assume if there is a work done on system, and work done on system, which is being done on the system, means compression. If you will do work on the system, definitely it will cause decrease in the volume, and it is compression, and this compression work is positive. If this work is expansion work, it will be work done by system. Work is done by the system, and this work is negative. It is considered negative sign. All right. And here are some limitations of the first law of thermodynamics. It never explains the mass energy relationship. How mass is converted into energy, it is never explained by first law. Also, it does not tell us about the direction of flow of energy. What does it mean? It says in which direction energy is being flowed. From where to where energy is being transferred. It is not at all explained by first law. It also does not tell the spontaneity of the process. Now, I would like to ask you a question, students. What do you mean by spontaneity? What is the meaning of spontaneous process? What do you understand by spontaneous process? Spontaneous processes are those which take place by their own. Those processes which take place by their own without involvement of the external agency are called as spontaneous process. Now, first law of thermodynamics, which is du is equals to q plus w. Now we shall discuss how this first law of thermodynamics looks like for various process of thermodynamics. In the last class, we studied about the various processes like isothermal, adiabatic, isobaric, and isochoric. Now, in this class, we apply this plot for various processes, and we shall begin with isothermal. See, in this isothermal process, what do you mean by isothermal? Isothermal means when temperature remain constant, and when temperature is constant, change in temperature is zero, and eventually change in internal energy is also zero. Now, if you will apply this condition to the first law of thermodynamics, it will be 0 is equals to q plus w, which finally lead to the q is equals to minus w, or w is equals to minus q. And formula of q we already know, w we already know. So by applying this, q will be this minus 2.303 nRT log V final upon V initial. This is how you can calculate heat in isothermal process. While for the adiabatic process, do you remember what is adiabatic? Adiabatic simply means no exchange of heat. There should be no exchange of heat, which means Q should be equal to 0. And when Q is equals to 0, du will be equal to W. So du will be equal to W means change in internal energy is directly equal to the work done. What is this WAD? It is work done in adiabatic process. So the change in internal energy is directly equal to the work done in adiabatic process, right? So you know that adiabatic process is the process in which heat is not allowed to enter or leave the system. No heat exchange is there. Q is 0. So this is how first law of thermodynamics looks like for adiabatic process. What about the isobaric? Students, do you know what is isobaric? Do you remember? Isobaric processes are those in which pressure remain constant. Now if pressure is constant, definitely change in pressure will be 0. When change in pressure is 0, nothing will be 0. So in this case, in this plot, first law of thermodynamics, no expression is 0, and it will look exactly like this. du is equals to q plus w. W is minus p delta v, and this, what is this qp? This is heat at constant pressure. And this is how we express the first law of thermodynamics for isobaric process. In the coming classes, when we will solve some questions, numericals for the thermodynamics. We will use these expressions while solving those questions. Another one is the isochoric process. Do you remember what is isochoric? Isochoric is the process in which volume remains constant, and if volume is constant, obviously delta V will be 0. So change in volume, students, change in volume will be 0. Change in volume will be 0. So du is equals to, see, when change in volume is 0, work done will be 0, because work done is what? Minus P delta V. And if delta V is 0, eventually work done will be 0. So this component will be 0 here. And this first law of thermodynamics will look like du is equals to Q. So whatever the change in internal energy will be equal to the heat directly for isochoric process. This QV is the heat at constant volume. Now we will discuss some type of chemical reactions. After studying the first law and the expression of first law and how first law looks like for the various process, we shall discuss about the type of chemical reactions. See, my dear students, chemical reactions could be of two types on the basis of energy. As far as the energy is concerned, they are of two types. Exothermic. I believe you must be knowing already what is exothermic. This is a chemical reaction in which there is an evolution of heat. Heat is released. Heat is released by the system. Heat is being released when reaction take place. Say for example, N2 plus 3H2 gives 2NH3 plus 92 kilojoule. What is the meaning of this plus 92 kilojoule? See, in this reaction, ammonia is appearing as a product, and as like ammonia, some heat is appeared as a product. So heat is appeared means released, evolved during the reaction. When heat is released, definitely enthalpies of the product will be lesser than the enthalpy of reactant. In simpler terms, you can understand energy of the product will be lesser because whatever the energy was there in reactants, some is being released. Some is being released during the reaction. So final energy of the product is definitely lesser than reactant. And the delta H, change in heat, will be enthalpy of product minus enthalpy of reactant, and that will be negative. So for the exothermic reaction, enthalpy change is negative. And this is how we represent it graphically. In this graph, we take here enthalpy, and we take here progress of the reaction over the x-axis. Over the y-axis, we take enthalpy. This is the condition of reactant. This is the position of reactant. Here at this position, this energy is the average energy of reactant molecules, and this is intermediate transition state. So reactant goes to the transition state, and when finally convert into product, you see in this graph, position of product is lesser than position of reactant in terms of energy, which means energy is being released, and this energy, which is the average energy of products, and this additional required energy to complete the reaction is called as activation energy, energy of activation, EA. It is represented by EA, which means energy of activation. Then endothermic reaction. It is a chemical reaction which occurs with the absorption of heat from the surrounding, and it is known as the endothermic reaction or the endoenergic reaction. Means energy is being absorbed. When energy is being absorbed, you see it is subtracted from the products, means it is added in the reactants. So when reaction take place, same like reactants are consumed, some energy is also consumed. It is being absorbed, and here enthalpy of the product will be greater than enthalpy of reactant because energy is being absorbed. In this case, definitely for sure enthalpy change will be positive. So here delta H will be positive. And this is the graphical representation of the exothermic reaction. Now you see, if this is the position of reactant, see the position of product is higher in energy in comparison to the reactant, because energy is absorbed, delta H is positive, so the position of products is higher in energy in terms of the in comparison to the reactant in terms of energy. Now the question is how to calculate the change in internal energy, delta U. So measurement of the energy changes are associated with the chemical or physical processes by an experimental technique called as calorimetry. Students, this calorimetry you will study that in depth detail in physics, but I shall also tell you something about the calorimetry. Calorimetry is the experimental technique in which we measure the amount of energy which is being involved in any chemical reaction. It may be evolved or it may be released. So the heat evolved in the process, it can be determined by the temperature change, because you know, whenever heat released, it appears in terms of the temperature. Heat is released, temperature increases. Heat is absorbed, temperature decreases. So we measure the change in temperature under two different conditions. Number one, we do it at constant pressure, keeping the pressure of system constant, and we call it QP. QP is the heat which is being measured at the constant pressure, and simultaneously we also calculate constant volume. Constant volume stands for where volume is constant, QV. Absorption of heat at constant volume can be measured in a device called as bomb calorimeter. Students, this is the device bomb calorimeter in which we calculate the change in energy at constant volume, and the energy changes associated with the reactions are measured with no work done, because at constant volume P delta V, which is work done, is 0. So basically no work done is involved at the constant volume. See, this is the diagram of bomb calorimeter. In this diagram you see there is a small chamber called as bomb. In this bomb we proceed the reaction, and whatever the heat released during this reaction, it comes out from the bomb and changes the temperature of this water which is placed just outside the bomb. Here is the thermometer which is used to measure the change in temperature, and this is stirrer, so that we make sure that the heat which is released is distributed in the entire water thoroughly. And we take the sample in the bomb. We have this firing leads to carry out the reaction. This is the oxygen inlet. If oxygen is required for the combustion or the reaction, then heat is released, which is transferred to the water, which increases the temperature of thermometer. We measure the change in temperature of thermometer, and by measuring it, by applying formula Q is equals to ms dt, change in temperature, mass of water and specific heat, we calculate how much heat is being transferred to the water by performing this reaction inside the bomb. And this is how we calculate the change in internal energy. So the temperature change of calorimeter by the completed reaction is calculated at QV. Now heat of combustion is Z into theta into m upon small m, and it is in calories. Now what are these signs? Z is the heat capacity of the calorimeter and also the water, because both are involved here. Theta is the increase in temperature measured by the Beckmann's thermometer. We don't use this here doctor's thermometer. We use the Beckmann's thermometer. By using this thermometer, we calculate the change in temperature. Small m is the mass of substance, of course in grams, and capital M is the molar mass of the same substance. Molar mass of the same substance, and small m is the given mass or involved mass in the bomb. Please make note of that. Then we go for the change in enthalpy measurement. Like we did change in internal energy. Enthalpy, the measurement of heat change at constant atmospheric pressure. We always calculate change in enthalpy at constant pressure. In the previous class also I told you that enthalpy is also called as heat at constant pressure. And heat at constant pressure, why we call it heat at constant pressure? Because it is calculated at constant pressure. So the heat of reaction or the heat content or the total heat or the enthalpy, all are same. It is calculated at constant pressure. This heat could be absorbed or it could be evolved. It could be released. In an exothermic reaction, heat is released. Then QP is negative and delta H is also negative. In an endothermic reaction, heat is absorbed. So QP is positive and delta H is also positive. So for the exothermic reaction, please make note of that, students. This is third time I'm telling you this today. For the exothermic reaction, delta H is negative, while for the endothermic reactions, delta H is positive. And enthalpy change, the enthalpy change accompanying a reaction is called as reaction enthalpy. So what is reaction enthalpy? It is sum of the enthalpy of product minus sum of the enthalpies of reactant. Whatever the total sum of the enthalpy of the products, summation minus summation of the enthalpy of reactant. And we do it along with the stoichiometry. AI and BI are the stoichiometric coefficients of the products and reactants respectively, which means if in any reaction there is an involvement of 2 molecules of ammonia, then we will multiply its heat by 2. We also use their stoichiometric coefficients. For example, for this reaction, CH4 plus 2O2 gives CO2 plus 2H2O. If you need to calculate the change in enthalpy, then what are the products? CO2 and H2O. So enthalpy of CO2 plus twice of the enthalpy of water, because 2 water molecules are there. See, what are the coefficients? 1, 2, 1, 2. So we will use 1 for CO2, 2 for water, minus summation of the enthalpy of reactant. What are reactants? Methane, 1 molecule. Oxygen, 2 molecules. So we will multiply its enthalpy by 2. And enthalpy change is a very useful quantity to calculate the temperature dependence of equilibrium constant, because relationship between equilibrium constant and temperature is correlated with the heat of reaction. It is correlated with the heat of reaction, delta H, enthalpy. I hope you are understanding this topic now. Now, standard enthalpy of reactions. Enthalpy changes during the phase transformation. What is the standard enthalpy? Whenever we perform any reaction under some certain conditions called as standard conditions. So if the enthalpy change for the reaction, when all the participating substances including product and reactant, they have taken at their standard states, then heat involved is called as standard enthalpy, which is represented by the naught sign, delta H naught. And what are the standard conditions? Temperature should be 298 Kelvin, pressure should be 1 bar, and if concentration, if any substance is in aqueous form or the liquid form, concentration should be 1 mole per liter. If these 3 conditions are being followed, it is called as standard condition. And we calculate the enthalpy change during the phase transformations. Phase means where the physical states are changed. See, when liquid is converted into solid, it is called as freezing. And when solid is converted into liquid, it is called as either melting or fusion. Similarly, when liquid is converted into vapor, gas, it is called as vaporization. And when gas or the vapor is converted into liquid, it is called as condensation. But if you bypass the liquid and you convert the solid directly straight away into the gas, this process is called as sublimation. And now we shall discuss different kind of energies which are involved in these such processes. What is the enthalpy of fusion? Enthalpy of fusion is the enthalpy change that is accompanied during the fusion of 1 mole of solid without change in temperature at constant pressure. So at constant temperature and pressure, whatever the amount of energy is being absorbed for the conversion of solid into gas is called as enthalpy of fusion, delta H fusion, conversion of solid into liquid. Another one is enthalpy of freezing. Freezing means solid is converted into liquid, is converted into solid, it freezes. So enthalpy change that is accompanied during the freezing or solidification of 1 mole of liquid without change in temperature at the constant pressure is called as enthalpy of freezing. Solidification, conversion of liquid into the solid, like this one, and this is also absorbed. This is also absorbed heat. The enthalpy change that is involved during the vaporization of 1 mole of liquid to the gas. Now what we are doing? We are converting liquid into the gas. In order to convert liquid into the gas, we have to supply some energy. So it is positive energy and called as enthalpy of vaporization, conversion of liquid into gas. Enthalpy of condensation. What is enthalpy of condensation, students? When gas is converted into liquid. This is released energy. Conversion of liquid into gas is heat absorbed, and here it is released energy. So it is negative sign. This energy is released energy for conversion of 1 mole of gas to a liquid without change in temperature, and of course at constant pressure. This is heat of sublimation. When solid is directly converted into gas, this also positive energy, heat is absorbed. For example, there is a sublimation of CO2, dry ice, where 1 mole of the solid is directly converted into vapor at constant temperature and pressure, is called as enthalpy of sublimation, delta HS or delta H sub. And finally, in the end of the session, students, these are some numerical values for the different kind of heat, sublimation and fusion, vaporization for different substances. I don't want you to memorize them. Just go through them. Just go through them once. They might help you sometime. So this was about the today's session of first law of thermodynamics and the different kind of energies and heat changes. We shall continue this class in the further coming lectures, and I shall tell you about the second law and remaining topics in the coming classes. I hope you enjoyed the today's class. Please keep coming and keep studying.